Okay, this video is to cover the magnetic levitation experiment. If you didn't get the notes down about the experiment, they're there now, so you can pause the video and get them down. The results, this is what we drew in class. Just remember we had the two supermagnets in the plastic tube, and the top magnet levitated where its weight force was balanced by the magnetic repulsion. When we added a mass to the top of that magnet, the height of rotation dropped, and that was because this magnet had to move to a closer position, once again with the magnetic force balanced out the weight force, but this time the weight force being bigger because it was mass 1 plus mass 2 together. We also saw that when we had the ring magnets on the skewer, when we had two magnets there being repelled, the levitation height was 3 centimeters. When we had the three magnets, this height dropped down to 2 centimeters, and that one at the top stayed at about 3 centimeters. So let's look at why that is. Look at these two skewers. In the first situation, we have the top magnet and the bottom magnet. Both magnets have a weight force. This is magnet 1 and its weight force is m1g. This is magnet 2 with a weight force m2g. They've got a magnetic repulsion as well. Their north poles are facing each other. So this one has got FB12. That means the magnetic force from magnet 1 acting on magnet 2 is going upwards, repelling. And this one here, FB21, the magnetic force from magnet 2 acting on magnet 1 is a downwards force. Now, this bottom magnet is resting on the support, has a reaction force, and that reaction force exactly balances out the weight force at FB21, and therefore it's still. This magnet here, it comes to rest at a position where its downwards weight force is balanced by the upwards magnetic force, so it levitates at a height d1, where FB12 is equal to m2g. In the second situation, we have the three magnets, called this time magnet 1, magnet 2, magnet 3. All I've done now is put their three weight forces on, m3g, m2g, and m1g, and these magnets are pretty much the same size and same mass, so those three forces should be the same. However, now let's start looking at the actual magnetic forces in play as well. So let's look at the first two magnetic forces, the magnetic force between magnets 1 and 2, FB12, the magnetic force from magnet 1 acting on magnet 2, and the magnetic force from magnet 2 acting on magnet 1. It's a force pair, both those forces are the same size. I've labelled them FB12 star and FB21 star because they are different forces to the two forces here. Because the height's different, those forces are actually a bit stronger than the previous ones. The next thing is, let's think about the forces between magnet 3 and magnet 1. If you look at the arrangement of north-south, north-south, you'll see the top of magnet 1 is a north and the bottom of magnet 3 is a south. Therefore, they've actually got a slight attraction force to each other. So FB13, the magnetic force from magnet 1 acting on magnet 3, is down, and FB31, the magnetic force from magnet 3 acting on magnet 1, is a little bit upwards. The third force we're going to think about is the force between magnets 2 and 3. And now they've got two souths facing each other. So therefore, magnet 3 is going to be repelled upwards and magnet 2 is going to be repelled downwards. So FB23, the magnetic force from magnet 2 acting on magnet 3 is upwards, and FB32, the magnetic force from magnet 3 acting on magnet 2 is downwards. So that's all the forces now acting on these magnets. We're mainly going to focus on magnet 2 and magnet 3. Obviously there's a reaction force here. This reaction force is going to be a bit less than over here because of the fact that it's got a little force acting upwards. But we're going to focus on these two heights. Now here we've got D2. This height here was less than D1. The reason being, M2, this magnet here, will levitate at a height where FB12, this upwards force, exactly balances out these two downward forces. Now, because FB12, this force here, had to be bigger than this original FB12 because it had to balance out two forces as opposed to one, because that force had to be bigger than the original force, it had to come to a lower levitation height. So the height had to be decreased because the magnetic force actually increases as distance decreases. So to make this force bigger, to balance out these two forces, this height had to be less than here, so D2 is less than D1. Looking at this top magnet though, magnet 3, this force here, FB13, this little downwards attraction force towards this magnet is very weak due to the big distance between magnets 1 and magnet 3. But anyway, magnet 3 levitates at a height where this upwards force, FB23, exactly balances out its two downward forces. First of all, FB13, which is the attraction to magnet 1, and also its weight force. Now, because we said this force is very, very, very small, that means this force, B23 or B23, is pretty much the same as the weight force of magnet 3. And therefore, this force is less than this force, and therefore this magnet can actually be a bit further away from that magnet because that force balance, that force here will balance that weight force at a bigger distance than this one here because that force only needs to be less. So that explains why D2 was less than D1, but D3 and D1 were pretty much the same size. Last thing to look at is some of the questions you've got to do on page 14 of your booklet. It's got a little graph here, and this graph shows you that the force, the magnetic repulsion force or magnetic attraction force, versus the distance. In this case, the repulsion force. We've got two north poles facing each other, and the key concept behind all this maglev stuff is that magnet 1, the top magnet, will float at a height where its weight force is balanced by the repulsive magnetic force. Now, as you bring the magnets closer together, as distance gets smaller, the force of repulsion gets bigger, and as the magnets get further away up this axis here, the repulsion force gets smaller. This curve shows you that as the distance is very small, the repulsion force is very big, so it's further along this way, but as the distance is very big, the repulsion force is very small. And this curve shows that if we plot the force, the weight force here, this is the weight force here, m1g, we know it's going to levitate where the repulsion force is equal to the weight force, and so that means it'll levitate at this height d1, where this magnetic repulsion force is balanced by the weight force. But it said in your notes that you could have another magnet, M2, which has got less mass. If this magnet had less mass, its weight force is going to be less. Its weight force is going to be further down on the force scale. So the distance at which it will levitate will be here, this distance here, a bigger distance. D2 will be bigger than D1 because the force required is less, and therefore it will levitate at a distance further away from the magnet. The other case was magnet 3. Magnet 3 was more massive, therefore its weight force is bigger. It comes further on the force axis. Where that magnetic force balances that weight force is at a much smaller distance, so it will fall down closer before it gets levitated because it needs to be closer for that magnetic force to balance the weight force. The next part was to sketch a curve showing a stronger magnet. Well, if you've got a stronger magnet, it's going to have a greater force at all distances. So at very small distances, its force will be bigger, and at very big distances, its force will be bigger. So that should just be a regular curve. It shouldn't probably get further and further away. It's just supposed to be a curve higher up, as in bigger force for the same distance. So where will those three forces be now? We've still got weight force m2g, still got weight force m1g, still got weight force m3g. Those three magnets will have the same masses and therefore the same weight forces. Where will they levitate now? Well, they'll all levitate at higher distances or at larger distances because m2g, its weight force is now balanced at this distance away, d2 slash. And m1g, magnet 1, it will now be levitated where its weight force balances that magnetic force, which is at a bigger distance, d1 slash, and same for magnet 3, it will levitate at a higher distance. So from this, we should be able to make two conclusions. As the magnet strength increases, what happens to levitation height? So comparing our two magnets, the strong magnet curve, the pink curve, versus the weaker magnet curve, the black curve, what happens to levitation height when we change the magnet strength? And also, the magnet mass, as we made the mass bigger, remember that mass 2 is less than mass 1, which is less than mass 3. As the mass got bigger, what happened to the levitation height? What happened to this height as we increase the mass? We should be able to make those two conclusions now.